Hello, everyone. I'm Damon Barnes. I run technical marketing in the promotion organization at the Bluetooth Special Interest Group. Today, I'm going to provide an overview of Bluetooth channel sounding. During this session, I'm going to cover a number of different topics. I'll start by reviewing recent Bluetooth technology feature enhancements and share some applicable market data. From there, I'll provide a quick refresher on what is Bluetooth channel sounding, as well as how it fits into the portfolio of Bluetooth device positioning features. Then we'll get into the technical overview and highlight some of the key points to be aware of. After that, I'm going to share some early implementation testing results from a couple member companies. We'll close with an update on early industry support and how Bluetooth channel sounding rollout is shaping up thus far. Let's get started. To start, let's go through a short overview of the major Bluetooth technology feature enhancements over the last several years. In 2016, we introduced two new PHYs, the LE2M PHY for higher speed, and then the LE coded PHY for longer range. In 2017, Bluetooth technology added mesh networking, enabling large-scale device-to-device communications, for example, networked lighting control. Then in 2019, we added direction finding for location services use cases such as real-time locating systems. Beginning in 2020, we began the rollout of Bluetooth LE audio, which would also enable Auracast. In 2023, we standardized very low-power, large-scale device networks, such as those used for electronic shelf labels, with the periodic advertising with responses feature. Now, here we are in 2024, and we just released Bluetooth channel sounding. We think channel sounding is going to have a significant impact on a wide range of Bluetooth use cases. Now, let's briefly talk through some of the Bluetooth market data to highlight the potential impact that these innovations stand to make, and also I'd like to point out the market opportunity for Bluetooth channel sounding. What we're looking at here is the Bluetooth technology growth forecast over the next 5 years. With over 5 billion devices shipping next year, Bluetooth technology is the most widely deployed wireless standard in the world. ABI Research projects 7.5 billion Bluetooth devices will ship in 2028. That represents an 8% compound annual growth rate over the next 5 years. This is a strong growth forecast and a massive install base. Here's an additional point I want to make. Many of these devices stand to benefit from Bluetooth channel sounding. In 2024, more than 1.3 billion Bluetooth connected products are predicted to ship. In 2028, more than 2.9 billion Bluetooth connected products are expected to ship. This is the market opportunity for Bluetooth channel sounding, which again is massive. Now let's get into the refresher on what is Bluetooth channel sounding. At a high level, Bluetooth channel sounding is a secure, fine-ranging feature that brings true distance awareness to Bluetooth connected devices. True distance awareness can enhance the performance of any Bluetooth connected product. I mentioned previously, but to reiterate, today that's more than 1.3 billion Bluetooth connected products. In 2028, that could be more than 2.9 billion Bluetooth connected products. When it comes to the use cases, channel sounding will have an immediate impact on Find My and Digital Key. But what happens when you make any Bluetooth connected product distance aware? You suddenly have a transformative possibility for all of these Bluetooth connected devices. For instance, Bluetooth hid devices such as mice, keyboards, and game controllers could automatically switch between active and inactive states based on their distance from a smartphone, tablet, or laptop, for instance. For Bluetooth HMI solutions, adding Bluetooth channel sounding can enhance personnel safety by only allowing their usage from a safe distance. Likewise, Bluetooth device networks, such as those used for wireless lighting control, can self-optimize their configuration to enhance performance. The opportunities are really limitless. As I mentioned, the Bluetooth channel sounding feature brings secure, fine-ranging capabilities to Bluetooth technology. Regarding the fine-ranging feature, Bluetooth channel sounding utilizes a well-established wireless ranging method called phase-based ranging, or PBR. Also, there are multiple security features available to mitigate against the risk of known wireless ranging attacks, such as spoofing and man-in-the-middle. I'll share more on that later. Here's a point to reiterate though. With more precise distance measurements, Bluetooth connected devices are able to gain true distance awareness. I mentioned that once before. That means a Bluetooth device can better understand its position or location relative to other devices. As far as the performance goes, Bluetooth channel sounding enables centimeter level accuracy, meaning we're measuring within tens of centimeters of the actual distance. Over the last several months, we've been working with the member community to have them conduct performance testing. Today, we're going to be sharing early implementation results that are reporting plus minus 20 centimeter accuracy at up to 100 meters. At distances of less than 5 meters, we have a member company reporting close to 10 centimeter accuracy. That's a great result, especially when you consider these readings are from pre-standard implementations. And we think it's quite likely that performance is going to improve as these implementations mature over time. Now let's run through how Bluetooth channel sounding fits into the portfolio of Bluetooth device positioning features. Bluetooth device positioning enables one device to determine the presence, the distance, and the direction of another. This gives Bluetooth devices the ability to understand their location in relation to each other. These capability areas have allowed Bluetooth technology to deliver flexibility unlike any other positioning radio. Bluetooth device positioning features can be summarized as follows. For presence, the feature is Bluetooth advertising. This is where a transmitting device broadcasts its presence to scanning devices within a general area or presence. We are saying the device is here, it's on premises. For distance, we now have two features, of course. First is Bluetooth RSSI. RSSI enables a receiving device to estimate the distance to a transmitting device by measuring the power level of the received radio signal. RSSI gives us approximate distance estimations, which we now label as coarse ranging. And of course, Bluetooth channel sounding makes precise distance measurements possible. That's our fine ranging. Then when it comes to direction, that's where Bluetooth direction finding comes in. This is where a receiving device determines the direction of a signal from a transmitting device. Direction finding tells us the device is over there. To reiterate, this is what you can think of as the portfolio of Bluetooth device positioning features. I'd like to provide some additional context about these Bluetooth features because there are some similarities and differences to be aware of. When comparing these features, we look at the feature in terms of the following attributes: its purpose, the key performance metric, and connectivity. That is the feature connection-oriented or connectionless? Here's how we lay it out. The purpose of Bluetooth channel sounding is to measure device distance, of course. Channel sounding provides fine-ranging measurements at plus minus 20 centimeter accuracy of actual. Channel sounding does require devices to be connected to one another, so it's connection-oriented. RSSI is also a device distance measurement feature. However, we quantify measurement accuracy within a percentage for RSSI. That is plus minus 20% of the actual distance, because there is accuracy degradation as the distance between the devices increases. RSSI can be used when devices are connected and also in connectionless scenarios. Direction finding is a little bit different, of course. Here we're determining device direction, and again, it's over there. Thus, the performance metric for direction finding is going to be degrees, typically plus minus 5 degrees. Direction finding can be used when devices are connected and also in connectionless scenarios. Lastly, of course, there's advertising. It's used to determine whether a device is currently present at a location or premises. Advertising can be used to determine presence at distances greater than 100 meters. Advertising is also a connectionless feature. Now let's turn to the technical overview portion of the presentation. I'm going to start with a summary of how Bluetooth channel sounding works technically, offering just a little bit more detail than what we've offered before. Then I'll touch on the ranging methods. We'll take a look at how channel sounding has impacted the Bluetooth LE stack as well. I'll also introduce some of the key points related to the Bluetooth channel sounding procedures that are introduced. Then we're going to go through antenna options. I'll also touch on Bluetooth channel sounding security at a high level. There are also going to be profile and service specifications for Bluetooth channel sounding that I'd like to introduce you to. Then I think it's also important to highlight a few key points on distance measurement algorithms. Then we'll wrap by sharing some of the performance testing results, and I'll also let you know where we stand with respect to early industry support for Bluetooth channel sounding. Okay, so how does Bluetooth channel sounding work? Bluetooth channel sounding takes place between connected Bluetooth devices in a one-to-one topology. There are two channel sounding device roles, the initiator and the reflector. The initiator is the device wishing to calculate the distance to another. The reflector is the device responding to the initiator. The application layer is what provides configuration choices and preferences that are suitable for the two devices. That's using channel sounding HCI commands. A channel sounding procedure consists of RF signal exchanges that produce phase and time delay data. Distance is calculated by a ranging algorithm using data passed by the LE controller to the application layer in HCI events. That's Bluetooth channel sounding operation at a high level. Now let's transition to the two ranging methods, which gets at how the signal exchanges occur. First, there's phase-based ranging. This method is used to produce the high accuracy distance measurements. With phase-based ranging, an initiator device, such as a smartphone, sends a signal to the reflector device, the door lock, which then returns the signal. The phase and the amplitude of the communications channel are what's being measured. The exchange is repeated across multiple frequencies. Distance between the devices is calculated based on the phase differences between the transmitted and received signals over those frequencies. That's phase-based ranging at a high level. Now on to the other ranging method, round-trip time, or RTT. Unlike phase-based ranging, where the phase can potentially be changed by an attacker, RTT is based on time of flight, and time cannot be reversed. RTT can be used as a countermeasure against sophisticated man-in-the-middle relay attacks. In RTT, an initiator device sends cryptographically scrambled packets to a reflector device, which then returns the packets. The distance between the devices is then calculated based on the time it took for the packets to travel back and forth. RTT can act as a secure distance bounding technique, providing independent distance measurements to cross-check the PBR measurements. This can significantly reduce the risk of man-in-the-middle attacks. By combining PBR and RTT, Bluetooth channel sounding enables secure and accurate distance measurements between connected devices. Now, let's take a look at the impacts Bluetooth channel sounding has had on the Bluetooth LE stack. Bluetooth channel sounding essentially adds a new physical layer to Bluetooth LE. This includes a new channel map. I'll share a little bit more on that later. At the link layer, you have a number of new procedures for Bluetooth channel sounding, as well as clock updates. We'll take a closer look at procedures in a little bit as well. There are also dedicated Bluetooth channel sounding HCI commands and events. Then there are also updates to GATT. The initiator and reflector roles are defined here, and 4 new security levels are defined as well. That's a quick tour of the changes to the Bluetooth LE stack. Now let's examine a few of these areas a little bit more closely. I mentioned just a minute ago that Bluetooth channel sounding introduces a new Bluetooth LE physical layer. Here's why I say that. There are new physical links for Bluetooth channel sounding. The channel sounding links are used to exchange the data that is to be used for distance calculations. Bluetooth channel sounding also introduces a new channel map. There are 72 channels with 1 megahertz spacing for channel sounding. No use of the primary advertising or guard channels. The hopping pattern remains pseudo-random. Then there is also a new physical transport, a new 2M PHY with a higher bandwidth symbol time product, or BT. The LE2M2BT PHY is only applicable to Bluetooth channel sounding and is not actually used as a data transport, only for distance measurement. In case you're wondering, that LE2M2BT PHY can be used to increase security. That's its main purpose. Now let's talk a little bit about Bluetooth channel sounding in the link layer. Bluetooth channel sounding consists of a combination of link layer procedures and a dedicated air interface protocol that creates an exchange of RF signals between two devices on multiple channels. This exchange is known as a channel sounding procedure, and it's what enables distance measurements. A channel sounding procedure consists of events, sub-events, and steps. They define a set of time and frequency slots in which two devices exchange a combination of RF signals. A procedure can contain multiple events. An event is a group of channel sounding sub-events that are anchored from a common LE connection event. Events can span multiple connection intervals. The sub-event is defined as a group of channel sounding steps that are associated with a specific timing. Steps are individual exchanges between two devices, such as the phase-based ranging exchange we discussed earlier. I think it's also important to emphasize that all procedure, event, sub-event, and step start times are anchored to a connection event in the underlying Bluetooth ACL connection. Also, the first Bluetooth channel sounding procedure instance, its first event, and sub-event all start at the same time, scheduled to occur at an offset from the selected connection event anchor point. Then the first step occurs at an offset from the start of the first sub-event. A couple more notes on sub-events. The channel sounding sub-event is the fundamental unit, which consists of steps. Each sub-event consists of two or more steps. Sub-events complete within a connection interval. They can be interlaced with other link layer exchanges, such as isochronous channels. There can be up to 16 sub-events per event. A few more notes on steps or step modes. In general, steps are either concerned with calibration or with the acquisition of low-level measurements that can be used by the application layer to measure distance. There are 4 step modes. Mode 0 is the first one, is used to calibrate one device to the other in terms of frequency and timing. Mode 1 is used to exchange round-trip time packets. Mode 2 is used to exchange phase-based ranging signals to measure phase and amplitude of the communication channel. Mode 3 is used to exchange both RTT and phase-based ranging measurements. Support for this last mode, Mode 3, is optional. Now let's tie together some of what was just covered. Two devices that wish to engage in a Bluetooth channel sounding procedure must first establish an LE-ACL connection. The connection is encrypted, so the communication occurs over a secure link. The initiation phase of a channel sounding procedure includes capabilities exchange and configuration settings between the two devices. Then the devices engage in the signal exchange over multiple channels. Events, sub-events, and steps are occurring here. Assuming a phase-based ranging exchange, Mode 2 steps whereby phase measurements will occur over a number of channels for a given time period are occurring. For the distance to be calculated, the initiator will process the IQ samples and timing data sent from the reflector. The reflector sends that data through a Bluetooth LE service. Then the initiator passes the data to the application to calculate the distance. One other topic I think is important to cover are antenna options. With Bluetooth channel sounding, there's a lot of flexibility. Devices can conduct a channel sounding procedure with one antenna each and get really good results. Bluetooth channel sounding does support multiple antennas, up to 4 paths. There are multiple configurations, 1 path, 2 paths, 3 paths, and of course 4 paths. The visual shows those antenna configurations. On support for multi-antennas. Multiple antennas can improve distance measurement accuracy. They provide alternate path options, which can help with interference mitigation. And then they also help with better distinguishing the shortest path when reflections are present. In the testing data that I'm going to share with you in just a bit, you'll be able to see some of the results with various antenna setups. Now let's turn to security. Bluetooth channel sounding has been designed for security. In this instance, we're talking about wireless ranging between connected devices. There are 2 main vulnerabilities we're guarding against here. Those are man-in-the-middle relay attacks and spoofing attacks. The security features I'm going to summarize are meant to act as countermeasures to these type of attacks. At this point, I do want to note that security can be a very complex topic. Bluetooth channel sounding has a tremendous amount of security built into it. What I'm going to share with you is by no means the exhaustive list of channel sounding security features. I'm going to organize the main list of security features into three main categories to make them easier to digest. Okay, the first security category relates to the new Deterministic Random Bit Generator, or DRBG. The DRBG helps with the following. It allows you to scramble the bit stream between the initiator and reflector devices. It can allow for randomization of payloads in packets, tone extensions, and antenna path selection. It also allows for randomizing sequences and packet lengths. The DRBG provides countermeasures to device spoofing attacks. The second is RTT, for secure distance mounting. I realize we covered this just a bit earlier, but a few more points to reemphasize. Secure RTT measurements can be used to verify phase-based ranging measurements. Attacking both methods without detection is regarded as highly complex by security experts. RTT helps guard against phase-based ranging relay attacks. Now to the third category. The Bluetooth Core Specification version 6.0 has defined a normalized attack detection metric, which will be commonly referred to as NATM. The NATM can help with the detection of unexpected bit transitions or phase changes in the received packets. The normalized attack detection metric prescribes a scale for how anomalies are classified. The NATM can be used to help guard against RTT relay attacks. There's a lot more to Bluetooth channel sounding security, but those are three areas I wanted to highlight. Now let's move to the higher layers. There are two GATT specifications in development for Bluetooth channel sounding, the ranging profile and service. They define the interoperable exchange of Bluetooth channel sounding ranging data for distance calculation. These specifications standardize how a distance measurement application can read ranging results from a remote device, as well as how to configure the desired content, delivery method, and ranging parameters. Here's a high-level example. A smartphone, the GATT client, requests ranging data from a door lock, the GATT server. The door lock forwards the ranging data to the smartphone through the ranging service. An application running on the smartphone processes the ranging data to produce distance calculations. At the application layer, that's where distance measurement algorithms reside. Bluetooth channel sounding provides standardized techniques to determine signal phase and time delay information, which can be used by the distance measurement algorithm to calculate distance. Bluetooth channel sounding does not define a distance measurement algorithm. Here's a key reason. The appropriate distance measurement algorithm configuration or setup may vary depending on the application. Thus, the inventors of Bluetooth channel sounding felt it would be best to exclude the algorithm from the channel sounding specification. That means the distance measurement algorithm can be sourced or developed independently. Another note, algorithm selection does not impact interoperability. Okay, we've now covered what is channel sounding and how it works. I've mentioned distance measurement accuracy a number of times now during this video. I do have some early implementation performance testing data to share with you. We had several member companies perform testing for us prior to channel sounding adoption. Thus, the results I'm about to share are pre-standard. Samsung LSI and Lambda 4 are the two member companies that partnered to provide the sample test results that I'm about to share. A few notes on their testing. They used prototype smartphones for the distance measurement testing. The environment was an outdoor parking lot with clear line of sight. The devices were stationary and mounted at a height of 1 meter approximately. The tests were run with 1, 2, and 4 antenna paths. The transmit power settings were 0 dBm and plus 10 dBm. A 90% statistical distribution for absolute error reporting was adhered to. On the results, I do want to reemphasize that these results are pre-standard early implementation testing. The first test setup was where the devices had 1 antenna each, so 1 antenna path. The transmit power setting was 0 dBm. If you first focus on the line of sight row, you see that all of the results are within plus minus 40 centimeter or better. I would like to note that the 40 centimeter reading at 10 meters was actually a bit of an outlier that's being investigated further. As you can see, the result at 1 meter was spot on, and then at 50 meters, it was within plus minus 20 centimeter, which are great results. On the second row, we have a back pocket setup where a person is obstructing the signal exchanges on one end. The back pocket testing results are very good as well. Of course, there is some performance degradation, and we had a bit of an outlier again at 5 meters this time, but the results were really good overall. Note at 50 meters, accuracy was still plus minus 50 centimeter. Now, the second test setup included one device with 2 antennas and the other one with 1 antenna. So 2 antenna paths for this testing round. The transmit power was again set to 0 dBm. Focusing in for a moment on the line of sight row, you can see we had excellent results. Spot on once again at 1 meter and then 10 centimeters, at 50 meters. Now in the back pocket scenario, we had good results here too. No outlier this time at 5 meters. All back pocket results were plus minus 50 centimeter or better. For the last testing round, the partners went with what you might call a high-end implementation. The setup included devices with 2 antennas each, so 4 paths. This time they cranked the transmit power up to plus 10 dBm. Focusing in again on the line of sight row, the results were really consistent once more. We were at plus minus 10 centimeter for all tests except for the test at 10 meters, which was still plus minus 30 centimeter. On the back pocket testing, we saw a little bit more variability as expected in the test results. However, we were still really good at 1 meter with plus minus 20 centimeter accuracy, and also at 50 meters at plus minus 50 centimeter. Let's wind down today with a quick summary of industry support for Bluetooth channel sounding. If you saw our press release and/or our quote sheet, you already know there's been really positive public support for the Bluetooth channel sounding feature. Companies like Samsung, Broadcom, Nordic, Texas Instruments, Infineon, Silicon Labs, Goodix, and T-Link were all really supportive on the chipset side. We've also received significant support from Denso, Lambda 4, Elysis, and Packetcraft. In Greater China, you saw both automotive connected car standards bodies made positive statements about Bluetooth channel sounding. And we're expecting product support on the enabling technology side before the end of the year in 2024. And then on the in-use product side, we're expecting those products to start coming through in 2025. Okay, so that concludes today's exploration of Bluetooth channel sounding. I hope you found this video informative. Thank you very, very much for the time today.